In 1740, the British HMS Centurion set sail for the South Pacific. After a very long journey, it reached the eastern coast of South America intact. Commodore Karlsen headed south to follow the 60 degrees south latitude westward around Cape Horn. But then a storm came up and pushed them back. Karlsen was able to roughly stay on the 60 degrees south latitude, but did not know how far west he was. After 58 days of sailing against the storm, he assumed to be safely in the Pacific, so he turned north to head to Juan Fernandez Island. But that judgment was wrong. He did stumble upon mainland very soon, so he had to turn west again before he could continue north. They were trying to avoid the coast of Chile, which was occupied by the Spanish enemy, and they desperately needed to reach the island for fresh water, as an ongoing illness has been continuously killing 8 men every day. So, they reached the latitude of Juan Fernandez Island on open water. As they knew that they were as far south as the island and were able to measure and keep that latitude, they could just follow that line until they reached the island. But with no means to determine the longitude, nobody knew whether they had to sail east or west to reach the island. So Karlsen just guessed that they were currently east of the island and had to head west. But after 4 days of sailing west, doubts came up. As they had not reached the island yet, they must have sailed in the wrong direction. So they turned back east. And they found land soon after. But it was not the island. It was the mountainous coast of Chile, occupied by the Spanish, which they did not want to confront. So they had to turn west again. Now knowing for sure on which longitude they were finally able to reach the island. But having wasted 2 weeks in search of the island, 80 more lives were lost to scurvy. This shows the big problem of that time. For the determination of longitude, the east-west position, an accurate clock is needed, as the Earth rotates 15 degrees towards the east every hour. This leads to the Sun being observed over the Earth's surface 15 degrees west every hour. Seeing the Sun at its highest point, the local 12 o'clock, doesn't help you on the open ocean if you don't know which time it is on your starting harbor. So you need a time reference to a known fixed place on Earth. Usually we use the UTC time located at the 0 degree Greenwich meridian. So when we observe the Sun at a local apparent noon and look at the carefully maintained UTC time, we get a time difference to our local 12 o'clock. This time difference can, after some small astronomical corrections, be directly multiplied with the Sun's 15 degrees per hour to determine the east-west distance to the Greenwich meridian, which is the longitude. This whole method of longitude determination by time was only available after the self-taught clockmaker John Harrison devoted his lifetime to create seaworthy clocks. And on the basis of his clocks, other clockmakers created chronometers that got sold in mass production in the 1780s. Only then the access to time got widely accessible at sea. And now, since the year 2000, we have a complete GPS network with full accuracy being publicly available. These satellites are sending us their onboard atomic clock time constantly worldwide. And affordable receivers determine a position that beats the accuracy of any human navigator. But George Karlsen, from our starting example, did not have access to any reliable clock on his journey, and could therefore only determine his longitude when he stumbled upon known landmarks. Navigating to a destination using only the latitude information as he did in the search of his island, is a sailing practice that dates back to the Vikings. With the so-called latitude sailing, they knew how to sail along a certain latitude and intentionally started their journey from a landmark at their coastline that was known to be as far north as their destination. So when a merchant wanted to head to the Viking settlement Horn in Iceland, he would choose the Halten Islands on almost exactly the same latitude for his starting position in Norway, and then just head straight west. But how could he check and correct that he was actually staying on that line? To answer this, let's go out on the water, close to these Norwegian islands. I have made a very primitive demonstrator of a sun shadow board as it is displayed in the TV series Vikings. This board swims in the water to be level with the horizon, while the ship itself is moving. Stick in the middle throws a shadow that varies in length. It shortens as the sun rises and is shortest at the sun's highest point. In order to determine the highest point, you would continuously observe the shadow until it starts to lengthen again and then take the highest angle or shortest shadow. So for a single shadow, you would take the board on your starting position, mark the shortest shadow at the day of your departure and draw a single circle for it. Then every day at noon, you could check if the shadow stays longer than the circle, which would be too far north, or if it would go inside the circle, which would mean too far south. But what I did here with my sun shadow board is that I added a general scale to calculate the sun's elevation from the stick height and shadow length. Basically a rudimentary sextant. Because what a real sextant does is also just measure the angle between the horizon and the sun. But the instrument itself isn't leveled in a bowl. So you have to aim at both the horizon and the sun at the same time. For this you have two optical pathways. One that goes straight through and another one that is coupled to a movable mirror. So you usually keep the horizon in the direct path and adjust the mirror to get the sun in your eye too. But since my sun filters are placed a bit weird, I do it the other way around and use the direct path for the sun and the adjustable path for the horizon. So, now we have gotten to know two very easy methods to determine a position on the globe with the sun. The latitude determination, measuring the sun elevation with a sextant or sun shadow, and the previous longitude determination by measuring the time difference to a reference time at noon. But the Vikings probably used the sun more as a compass to give them orientation instead of position. And in order to reliably track the sun's position, I present to you one last navigation device, the sunstone. The intention is to even find the sun when it was below the horizon or behind fog or clouds. Most likely the Icelandic spar, also known as calcite, was used. This stone splits light in two images of different polarizations. So when you put a dot on one side and look at it from the other side, you get one image with a vertical polarization and one image with a horizontal polarization. Now, if we hold that on the blue sky and start to scan the horizon, we noticed that these two images differ in color or intensity, and that this difference gets bigger and smaller. When both images have the same color or intensity, we end up either away from the sun or close to the sun. This is because the sky is polarized in circles around the sun. So we reach points of equilibrium here. But usually when the horizon is clearly visible, we don't have a very cloudy sky. So what we actually do on a cloudy sky would be to point our sunstone at a free patch of blue sky. It has to be without clouds. And we repeat our process again, looking for the differences. And when we found our match, one of our sides should be aligned to the sun. Now, let's do that again. We point our stone to a blue patch of sky. We rotate it around. We go to the extremes. We see that a color difference appears. And we try to make both points equal. And once we've done that, one of the sides should point towards the sun. Yippee!